Thanks. That's clear enough. Okay. So, yes, I changed the title a little bit. That's right. What I would like to talk about is a bit of an introduction to the different techniques that people use to investigate how the subduction process, or maybe more generally how plate tectonics changes dynamics throughout time. So before I forget, these are my co-workers down here. I'd like to thank them for collaboration. So in this talk, basically I've split it up in two parts. First, look at some dynamical models, theoretical, numerical models, and then look up some observations from the rock record. And hopefully then, in the end, I'll be able to say something about changing style of subduction through time. So we know that today subduction is one of the key processes on Earth. It basically governs plate tectonics. It's important. It's probably the most important part of plate tectonics. Without subduction, you can't have any plate tectonics. So the question is whether it always had a dominant role in the past as well. So let's start simple. The surface tectonics is related to the heat budget. Is there a stick or anything? Oh, there we go. Yeah, that's great. Is this? Looks like a long pen. Oh no, there we go. Okay. Okay, so heat budget related to surface tectonics. Today, the Earth is releasing heat about 36 terawatts or so, or 80 milliwatts per square meter, and about 20 to 50% of that heat being released is being replenished at the same time radiogenic in its interior. So 50 to 80% of the heat is not replenished and leads to cooling of the Earth. So that can be put in a very simple equation where the temperature of the Earth is basically T, and this is changing through time. Heat capacity, this equation says that the temperature change is due to radiogenic heating minus what escapes the heat through the Earth's surface. If we assume 20 to 50%, that's referred to as the Urey ratio, 20 to 50% of the today's surface heat flow. So today's surface heat flow is the blue line over here. 20 to 50% of that are the two red lines over here. So today we are over here. If we extrapolate this back in time, because of radioactive decay, we had more heating in the past. So these curves might blow up to this range here. And as you can see, if we make the rather crude assumption that the amount of heat escaping through the Earth's surface never changed through time, then if we go far back enough in time, we might have had more heat. Yes, sorry.
Could you just clarify that this isn't the total planetary heat loss?
No.
What do you mean by heat?
Good. Thanks. That's a good question. So the 36 terawatts is actually, the total heat loss is more like 44 terawatts. But about 8 terawatts or so of that is being produced inside the continental crust and immediately escapes through the surface into space. So that heat being produced is immediately lost and therefore doesn't really contribute to the heat budget of the Earth. So for these kind of simple calculations, it's the easiest way is to take it away from the heat production and also take it away from the surface heat flow. Yeah, thanks. So if we go far back enough in time, it might be that the Earth was actually producing more heat that it could get rid of, assuming that surface heat flow didn't change through time. So the question is, what do we actually know about the temperature change through time? So let's look at the observations. These are some early estimates. This is a more recent estimate of temperatures throughout the Earth history. These are Mantle temperatures. And they are derived from the primary melts from Mantle materials, or basaltic material. The composition gives us an idea about the liquidus temperature of those basalts, and these are then translated into a Mantle temperature. And the black dots here show those temperatures. So this is the key information to take from this plot. These are komatiites, which show a lot hotter Mantle, but these are normal basaltic material. So it seems to have dropped indeed by a few hundred degrees over time. So, and perhaps, and this is a little bit more speculative, perhaps it peaked in the late Archaean. It could have been the temperatures in the late Archaean were actually hotter than before that. But that's a bit speculative, perhaps. So, but, sorry?
Can't you also estimate that from continental freeboard uplift?
Well, the continental freeboard shows that kind of the Archaean continents didn't really get uplifted significantly through time, right?
You need to know continental growth and oceanic ocean continental freeboard.
Yeah.
No.
Because the demand for pools will only become more dense and the continents rise up.
As the mantle. Sorry?
I didn't mean to derail you.
Okay. So this equation again, you can put this. You can if these are simple equations, then this becomes a simple analytical exercise. You can come up with a curve here, but depending on the URI ratio, so the amount of heat production, depending on the surface heat flow model you take, you get different curves here. So each of these different curves is a different surface heat flow model. Don't want to go into the details of this, but the blue crosses are the same as the red dots on the previous slide. So these are the observations. And as you can see, you can easily fit those models to the observations, which is a bit unfortunate because it means we can't really distinguish between each of those dynamical models. And the difference between those models tells us about whether plate tectonics could operate or not.
Could you just go back to the previous slide?
Yes, of course.
I was just wondering about the Episodic data because I think there are two opposing models from Episodic formation. One is that the magma forms at low temperature under wet conditions, and the other high temperature under dry conditions. This is presumably the dry model.
Yeah.
Very low water content, so I'm sure that
A few years ago, there was maybe it settled down.
Well, might have been this study that suggested that perhaps those melts in general are formed under much more wetter conditions, and therefore you don't need as high mantle temperatures, but you can maybe get the same amount of melting and the same extent of melting using a slightly wetter mantle rather than just a very hot mantle.
Can I ask you just a general question? Do we lose any sensitivity in terms of being able to determine temperature?
Sorry, do we lose any sensitivity?
Do we lose sensitivity to being able to determine temperature to go back in time? In other words, conditions stop changing as much.
I don't think so, actually. I think it's just taking the sample and derive directly from it the melting temperature, and I think it doesn't really matter when that rock was being formed. I mean, you can use exactly the same principle, the same techniques to do this. You might lose some resolution in the timing of the rock.
Yeah, I guess what I was sort of meaning was if you get up to a certain fraction of partial melt, I was kind of wondering if you're building the compositions of the solid.
Oh, I see. I don't,
You're building then guess what the original temperature was.
I
Mark, you know?
don't know.
Yeah, if we build an algorithm
But we don't get anywhere near there here, of course. So.
This guy here is quite controversial among petrologists, I understand. It depends on, what do you think is an altered rock and what isn't. It's highly selective as to which materials you choose, and then how to translate that into
Which basalt you choose, you mean, or which melt products you choose?
both.
Okay.
So maybe I can also add the dynamic model, the parameterized mantle convection model is probably also very controversial.
That's right. So that is actually the parameter.
You reference Jeff Davis in 2009. You know that paper
Yes.
actually kind of dispute one of the basic promise of the Carlisle, which is the bending controls everything.
That's right.
And what we know now, bending, it only probably accounts for a relatively small fraction of viscous dissipation.
Yes. That's right.
And you get it back anyway when it's undone.
Well, it's plastic, you know.
So this parameterized convection model is the red curve in here that actually have some significant problems. It doesn't seem to fit to the data easily unless you use extremely high URI ratios, right? And this is...
That model is wrong too.
Sorry? The parameterized convection model is wrong.
Well, I guess there are certain physical processes
Yes.
that actually not being accounted.
Yes, exactly. Yeah, and yeah, that's true. So basically what this, so to explain more generally, this parameterized convection model is basically assuming that if you weaken mantle material, then everything gets weaker, and therefore the plates start moving faster. That means the Earth is cooling faster as well. So therefore, this curve becomes a little bit steeper, faster cooling. And if you go back in time, that means hotter temperature, which means even weaker and therefore even faster cooling. And this easily leads to a runaway effect that, as you can see, you can hardly extrapolate back to an early Earth unless you use a very, very high URI ratio to do this. So in other words, you start with a very flat line here to start with. Is that right? Anyway.
100 to 300 Kelvin over the late Archaean.
Yes.
Power, so you assume some heat capacity for the mantle, and then so what power is that? 5 to 15 terawatts or something like that? Your last slide, 100 to 300 Kelvin.
Well, that's just the observations. These are just the observation, 100 to 300 Kelvin. That's kind of, depending on which study you take, is what they think is the change in temperature of the mantle from observational point of view. So there's no models going into that system. These are purely...
You can translate that into a power if you know the heat capacity of the mantle? Heat loss rate, so power. So does it correspond to 1 to 3 terawatts, 5 to 15 terawatts, 10 to 30 terawatts?
Terawatts of heat loss, you mean?
Yeah, the mantle is cooling by 100 to 300 Kelvin.
Yes. Oh, sorry. Yeah. So you mean the total amount of heat that's being lost? You can calculate that over time.
The energy, but the power, the rate, right? Because you start off with 36 terawatts. So I'm trying to make a consistent story in terms of the power output. So is that 100, 300 Kelvin, 1 to 3 terawatts averaged over since the late Archaean when that temperature change occurred, or 5 to 15 terawatts, or?
No, it's more than the total heat output of the Earth. That's the whole point. The left-hand side term is larger in magnitude, or comparable in magnitude at the present time, to the H, or the Q, which is the...
That's right, because H is...
generation.
Yeah, because H is...
That's the whole point. So 100 degrees, I mean, that corresponds to 20 terawatts or something like that.
Okay. Well, okay, so those are the kind of studies that relate the heat budget to perhaps the tectonic history at the surface of the Earth. Now, perhaps another approach to take is to look at dynamical models to see how actually a subduction process is really changing through time and see if we can learn more from that. So if you change the mantle temperature, there's basically two consequences if it comes to the subduction process, and I will show this in a numerical calculation later on. But there's two key parameters that change significantly when you change the mantle temperature. And one is the buoyancy, which means that when you have a hotter mantle, you produce more melt. The melt is buoyant relative to the density of mantle material. And therefore, the average density of the subducting plate is decreasing. These are estimates for the thickness of the oceanic crust, where we have a 7 kilometer today. It might have been up to more than 20 kilometers or so when the mantle was 300 degrees or so hotter than it is today. So that's the buoyancy. And in terms of strength, we'd expect a different strength of material as well. I'll get into it in the next 2 slides or so. I get into a little bit more detail about this. So first the buoyancy. So as I said, more melting leads to a thicker crust. It also leads to a thicker layer from which the crust is extracted, the residue layer. So these layers are getting both significantly thicker, and both crust and residue have a lower density than original mantle material. And therefore, the average density of the slab goes down. You can This is a calculation by Jeff Davies in the early 90s, suggesting that actually this could easily lead to a situation where an oceanic plate arriving at a subduction zone is still not negatively buoyant and therefore would never sink. In other words, there wouldn't be any slab pool available to drive subduction. And without subduction, there wouldn't be any plate tectonics. So perhaps a present-day example of this is on Java, which does actually have a thicker than normal crust, and doesn't seem to subduct. So now this is not the whole story. Basalt transforms into much denser eclogite when you bring it down, so that might actually solve the whole problem of buoyancy, except for the fact that in order to form a basalt, in order to form an eclogite, you first have to subduct it to significant depth, at least 40 or so kilometers. But perhaps if basalt remains metastable, it might be significantly deeper. So it's the problem that in order to form eclogite, you first need subduction to start with. So it's a bit of a chicken and egg problem here. As I said, mental strength is another issue, another parameter that is probably important, and there are two views on this. On the one hand, all that extra melting leads to a compositionally much thicker layer of a subducting plate. So the residue is dry, and dry material is generally stronger than not dry material. So we could expect significant strengthening of material by perhaps 1 or 2 orders of magnitude by complete dehydration of that plate. So we have a much thicker plate that is dehydrated. Now, such a much stronger plate would be harder to bend into the subduction zone. This is something that Shiji just brought up, and it was suggested that that could be fit with supercontinent ages, such that the Wilson cycle would significantly slow down if a lot of energy is required to bend things. And this can be seen in the timing between subsequent supercontinents, which, if you go back in time, apparently gets longer and longer. So that's one view. The opposite view is that actually plates become weaker over time. There's several reasons to assume that that is actually the case, but the most important one is probably that if you just simply warm up material by say 100 degrees, it would weaken it by roughly an order of magnitude. So 200 degrees, 2 orders of magnitude. That significantly adds up to the weakness of material. Another argument is the fact that the viscosity of crustal material is intrinsically lower than the viscosity of mantle material. So if we have a much thicker part of the oceanic plate being crust, then the overall strength of that subducting of that oceanic plate will be lower as well. And then there might be rehydration of the plate in bending when it enters the subduction zone, which might weaken the plate as well. So the plate strength is still not completely resolved. Actually, rheology is always one of the key uncertainties in geodynamical models, but it looks like plates are actually weaker rather than stronger if you increase mantle temperature. So put this all in some numerical models to see what actually the dynamics is showing us. So these are dynamical models that include that effect of buoyancy. So thicker crust. The crust is actually, for those of you, I'm not sure if you can see it, but the crust is shown as black and white material. Basalt is black, white is eclogite. The colors here show the strength of mantle material, where obviously blue is strong and reddish colors is much weaker. And what we have here is 4 different calculations. So this is one calculation for the present day situation, trying to simulate a subduction zone. And this second column is the same calculation, but for 100 degrees hotter mantle, and then for 200 degrees and 300 degrees hotter mantle. So just to illustrate what could happen if you increase mantle temperature over time, would the dynamics of subduction actually change? Oh.
So in those pictures, you have
Yes.
that red patch everywhere.
That's right.
Which is very low viscosity.
That's
Where
true.
do you actually get that number from? 1070 Pascal seconds. I'm talking about that little red.
Yes, that's actually something I imposed on each of these models. I imposed that. It's not because in order to do this fully self-consistently, you need to track the circulation of water into mantle wedges, and that's not really included in these calculations. But you're right. This is imposed. So imposed weak mantle wedges, as actually most of these subduction zones actually do, in order to provide enough decoupling between the overriding and the subducting plate. It's a necessary ingredient for any of these dynamical models.
The thermal structure and the physical structure of the subducting slab in each case is the same, it's just the mantle temperature that's changing?
It's the the thermal structure, because this is a dynamically self-consistent process. So if the plates move faster, they are younger when they arrive at the subduction zone. So the age is determining the thermal structure, and the compositional structure is determined by the amount of depletion. So in other words, the thickness of the crust and the hard basaltic layer underneath. So they're not the same in each of those models, but they should be consistent with the increase in temperature. Okay, so if we focus on the first two, we see, well, there's clearly some changes if you go from a present-day situation to 100 degrees hotter mantle. The key difference is that actually subduction, I didn't show the velocities, but the average velocities significantly go up when you increase the mantle temperature. And this is mostly due to the much weaker mantle. So the weaker mantle, and actually the weaker plate as well, the weakness leads to a faster plate motion, just like actually the parameterized convection models suggest. However, unlike the parameterized convection models, if you keep on increasing the mantle temperature, you keep on weakening the plates more and more and more. And at some point, the plates become so weak that they are too weak to actually withstand the extensional stresses that occur in the slab itself. And the slab, while it's subducting, is frequently breaking up, a process that we usually see, say, during continental collision or so. We in the numerical models at least, we see things like slab detachment, slab break-off after continental collision. But in these kind of processes, in these models, there aren't no continents subducting or entering or colliding. This is spontaneous slab break-off occurring when the mantle is hot enough, and therefore plates and the mantle are all weak enough. So that's a significant change in the style of subduction according to those models. Subduction doesn't completely stop, but it changes its style. If you increase that another 100 degrees, actually, this particular set of models doesn't work anymore. There's no way you can get subduction to work. It immediately leads to break-off, and subduction will not start again. Now, I have to admit that there is significant uncertainty in those models. This is the default model is the black line over here. This is the subduction velocity for different mantle temperatures, the average velocity of the models. This is a whole range of variation of all kind of parameters, mostly rheological parameters, but several other parameters as well. And as you can see, if you change those, you get different results. So there is uncertainty in there, but the general trend is in most models the same. You get an increase of velocity where it works most efficiently, and at some point the weakness of the plate starts to resist subduction, and actually the average velocity goes down again. This is some related study from a few years ago, Sitsova. They did it with a completely different type of model. They created fairly similar results in the sense that if you keep on increasing mantle temperature, you do find that modern subduction changes into something that doesn't look like modern subduction anymore, but at least there is some form of subduction still possible. But if you keep on increasing temperature, at some point that stops and subduction doesn't seem to work anymore. Again, in this study, it's related to the weakness of the plate. So not so much the buoyancy. As I argued, the buoyancy is perhaps a problem as well. While according to the numerical models, buoyancy isn't so much of a problem. It's the strength of the plate that seems to actually cause problems when trying to get plate tectonics working in a hotter mantle. So what does the rock record show us? Well, as you probably all know, there is not a huge amount of Archaean rocks left. And there are no rocks left other than individual zircons if we go further back than 4 billion years ago. So what can we learn from the rock record? Well, this is a study by Bob Stern, one of his papers that argues, it's a several papers he wrote on the similar topic. He tried to compile evidence for plate tectonics basically trying to find key characteristics of plate tectonics and see if we can trace those characteristics back in time. For example, passive margins, ultra-high pressure terrains, blue schists, ophiolites. And he finds that most of these key characteristics cannot be reliably traced back to, before the Neo-Proterozoic. Perhaps a few ophiolites longer ago, but in general, we don't find real good evidence for modern style plate tectonics before the Neo-Proterozoic.
This is simply a graph of what the half-life of preservation of various rock associations are.
Thanks. Yes, no, I wasn't really getting there, but you're right. Actually, I mean, I'm not saying that I agree with this view. You're right. This could well be a preservation issue, that we simply can't find these features because they have somehow disappeared over time.
The point I make to Bob is, I spent a lot of time in Tibet, and their collision started 50 million years ago. It's still, underway, and along the suture, the ophiolite is missing in more than half of the locations. Mm-hmm. So here's a kind of collision that hasn't even stopped, and already half the ophiolite is gone.
It's gone.
Wait a billion years, and it'll all be gone.
Yes. Okay. So so this could well be not.
It's fine-grained sediment.
Yeah. So you're right. This could mean that these features were all there back in time, but over time they have disappeared. What it could also be is that the subduction changed over time. It slightly changed, as for example the numerical calculations seem to suggest that the style is slightly changing, and therefore maybe we do not exactly expect the same features we find today. Maybe the features were there in some kind of modified form. Alternatively, if we go a long time back, if we look at the Zircons from the Hadean, we find that these suggest that continental crust was present back then, that there was liquid water at the surface of the Earth, and that this continental crust was somehow recycling back into the mantle. And at the moment, we do not really know of a lot of processes other than subduction that can actually provide this recycling of surface material back into the mantle. So this could be taken as the other view on this, that basically subduction almost has operated throughout the history of the Earth. Now, about the ophiolites, just to pick one of them out, it's been suggested that a 3.7 billion year old ophiolite exists in Greenland. More generally, people agree that about 2 or so billion years ago, we do have a significant number of ophiolites that are recognized. But we do have to see that ophiolites actually are more frequently occurring in the last billion years as they are before. And this could actually well be a preservation issue, as just brought up, or a change in style of plate tectonics. Okay, this is a study by Shirey Richardson from last year. They used diamond inclusions, so the little mineral inclusions sitting in diamonds and being shielded off from further evolution for a long time, ever since the diamond was formed. And interestingly, all the diamonds that are having an age older than 3 billion years seem to have periodicitic inclusions. So the inclusions also suggest this mantle material sitting inside the inclusion. So no evidence for some kind of plate tectonics there. However, the ones that are younger show both periodicitic and eclogitic inclusions. And the eclogite inclusions suggest that this is perhaps crustal material being formed near the surface and somehow made it back into the mantle, formed into an eclogite, and got stuck into the inclusions in the diamond. So this has been taken as evidence that perhaps plate tectonics started around 3 billion years or so. Structural evidence, well, linear features on a map are usually interpreted as some kind of form of subduction zone. This is a bit vague, of course, but if you think about present-day linear features such as the west coast of South America, long linear features could be interpreted as subduction zones. And these linear features over here in the Superior Province have been interpreted as accreted terrains along subduction zones. And if you take vertical cross sections perpendicular to this, you get studies like this, seismic profiles taken. They recognize dipping reflectors that have been interpreted as fossil subduction zones. This is again the example of the Superior Province. This is a slightly younger example from Finland. Okay, those features, we don't find them everywhere. We've got the East Pilbara, for example, which is an example where those features are not really observed. Okay, so the geochemical signature of continental crust is another indicator, perhaps, of the existence of a subduction zone. We know that today typical continental crust, so andesites, contains features that we recognize as an arc signature. This, as Rick was showing this morning, if you look at the trace element pattern and you put them in order of compatibility for a mid-ocean ridge, a shallow mid-ocean ridge, you'd expect a smooth line. And the red line over here is a typical modern continental crust, which is not very smooth. And the reason why it's not very smooth is because this probably includes fluids. And the fluids, some of the elements are fluid immobile, and they like to sit in the residue, whereas others like to go into the melt. And that causes the spiky pattern that we observe for most arc signatures, contrasting to mid-ocean ridge basalts. Now the gray dotted line on this plot is for Archaean continental crust, the so-called tonalite, trondhjemite, granodiorite. Although there are differences here, of course, there are clear similarities, and one of the similarities is the same spiky pattern can be observed for the Archaean rocks, which could be interpreted as that also these Archaean TTGs are actually formed under water-rich melting conditions. Now, that's not to say that that's necessarily a subduction zone. There are probably other processes that we can think of that cause some water-rich melting conditions. But if we zoom in a little bit more on the different type of TTGs, so these are different, these are all the TTGs, but then subdivided into different classes. And the classes are based on the tail on the right-hand side here. Some of them have a tail that goes down, and some of them have a tail that is horizontal. And this relates to what Rick was showing this morning, the fact that the distribution coefficients for different rocks is different. And for example, if garnet is present, the distribution coefficients for those elements on the right-hand side, the heavy rare earth elements, is very high. In other words, the heavy rare earth elements like to sit in the residue. They don't like to go into the melt. In other words, the melts are very depleted in those heavy rare earth elements. Now, the interesting bit about this garnet is that garnet is formed under conditions larger than, a depth larger than 60 or so kilometers. So not only are these TTGs formed under water-rich conditions, but the water has been brought down to significant depth as well. And this together has been taken as, well, possible evidence for subduction process, because we can't think of many other processes that can bring water down to significant depth into the mantle. Subduction metamorphism, one of the other key characteristics taken for subduction zone is the fact that we have paired metamorphic patterns. We find high geotherm and low geotherm metamorphism sitting close to each other. The low geotherm metamorphism is formed inside a subducting plate, where the geotherm is very low. But right behind the subducting plate, we've got the back arc region, which is very hot, and temperatures increase really rapidly with depths, and there we find a high geotherm. So there's two types of metamorphism sitting quite close together, and that's a key characteristic for modern style plate tectonics. If we go to the Archaean, we actually can't really find very low geotherms like we find for the modern day. And this is maybe what we expect for a hotter mantle. But we do find those paired, we do find more and more those paired metamorphic belts sitting close together, which might have been, which again has been interpreted as evidence for Archaean, in this case, Archaean subduction. Okay. Now the final thing I'd like to to suggest in this talk is the fact that maybe the style of subduction changed over time from a long-term continuous process of subduction that we have today to a more episodic style of subduction on a very short timescale, episodic style of subduction in the early Earth. And this is based in part on the calculations I showed earlier, the fact that slabs do not behave as a coherent, long-lived slab, but they tend to frequently break off. This frequent break-off is observed in the subduction velocity, which for this particular case, there's a wild variation of the subduction velocity through one single calculation. So this is only 10 million years, and throughout the 10 million years, there's a wild variation of the subduction velocity, and that is due to the frequent break-off of each of these slivers of the subducting plate that actually leads to a temporary stop in the subduction process. Now, this in itself could just be a model artifact, of course, but when I was talking to, who now is one of my collaborators, is Jean-François Moyen at EGU a couple of years ago, he suggested that actually he could recognize those temporary subduction signatures in the geological record as well. This is an example he gave me for the Abitibi region, where he said that, where he was showing that actually some of the magmatism that was observed had a clear arc signature, just like the trace element pattern I was showing you a few slides ago. And those are all those hashed areas over here, whereas other magmatism in the same region, but having a different timing, shows basically a clear absence of this arc signature. And he suggested that perhaps this could be a more plume-related or other geodynamic scenario-related melting process. So we see that there is some alternating pattern of subduction-related and non-subduction-related, or arc-related and non-arc-related magmatism, with a typical timing of just a few million years. Now, it doesn't seem to fit perfectly with the geodynamical models, but these together, we could take this as a suggestion that perhaps the subduction process was more episodic on a short scale. In other words, that subduction wasn't as continuous and robust as it is today, but it was more hesitant, more difficult to get going, and frequently stopped in time. Other regions seem to show a similar pattern, although the time resolution seems to be not as good as for the region I showed before. But what we have to do is to contrast this against modern style volcanism. This is an example of the subduction along South America, so the Andes, where we find actually a continuous record of arc-related magmatism for more than 100 million years. So this contrasts with the much shorter-lived periods of arc magmatism in the Archaean. And these are just a few other more recent examples as well. So that's really all I wanted to show in this short talk. So concluding remarks, subduction evolution, perhaps we can use thermal evolution to at least to constrain some surface tectonics. Modern style subduction from numerical models seem to be viable up to 150 or 200 degrees hotter mantle, but if you make the mantle even hotter, it starts to become very difficult. From a dynamical point of view, and the main reason is the weakness of the mantle material and the subducting plates. In the rock record, we seem to be able to recognize the subduction process very, very long time ago by looking at the zircons, ophiolites perhaps, structural geology, geochemistry of TTGs, and perhaps subduction was more episodic in style than it is today. That's it. Thank you.
Showing eclogite slab fragments trapped in the upper mantle transition zone.
Yes.
How long do you think those slab fragments would remain there? Would they be neutrally buoyant or anything like that?
That's probably one of the unrealistic features in this particular calculation. It seems like none of the material seems to sink into the lower mantle. So the phase transition, let me get back to that, Well, this one will do. So this is the 660 discontinuity, the phase transition occurring there to perovskite, which shows that which basically resists most of the material to go through. So conditions in terms of Clapeyron slope and.
But do you also have a viscosity?
There is a viscosity. No, there is no viscosity contrast in the. So there is a. It's assumed in terms of rheology, which is probably not correct, but in rheology it's assumed that all the three phases of the same material, so the olivine and the spinel and the perovskite, all have the same rheology, but there is an overall viscosity increase with depth due to activation energy. But there isn't a sharp jump in viscosity here at these layers. No, there isn't. It's just a phase transition, but probably the Clapeyron slope I took was something like minus 2.5 or 3 megapascal per Kelvin, so that might have been a bit on the high side. And the other thing is these are two-dimensional calculations. In 3D, it's slightly easier for material to penetrate through, because if part of it in the third dimension is penetrating, that might drag the rest of the material through as well.
Calculations with 3D flow models I've seen, where I wonder if your calculations would change if you had a much wider aspect ratio and went to the continental boundary, where you have 3D flow where there are, just mantle up and down wellings. So
yes,
it kind of gets into something that I don't know how well it's understood, that viscous coupling between the slab and the mantle flow. So the mantle flow could be carrying the plate in certain places. Sure, the subduction, the slab is going to determine the currents, but
yep.
So I just wonder what your comment on that is.
Yes, yeah. So
this break-off, is this kind of calculation more?
So these calculations.
For this kind of phenomenon?
Yes, yeah. Well, these calculations basically I'll try to set up as simple as possible in the sense that there wouldn't be strong convective currents if there wouldn't be any plates sitting on top. So it's mostly driven by the negative buoyancy of the plates. And there is, there is a Rayleigh number imposed which is non-zero. So it would, even without plates, it would start convection. But in this case, all the temperature contrast is sitting in the thermal boundary layer at the top. So it's that thermal boundary layer at the top that drives most of the convection, whereas the rest of the mantle in these calculations has a fairly homogeneous temperature distribution. So that doesn't really contribute much to the convection. In 3D, you can probably expect, some toroidal flow of material flowing around the slabs, and that might have a contribution as well. But I'm not sure if that's really important for this particular case. It might, of course, have an influence. What might be more important is the fact that this break-off of slabs is in a 2D model is assumed to be occurring in the third dimension all simultaneously, which obviously is probably not very realistic. It's more likely to form like a tear in a slab that starts at one end and propagates all the way to the other end. Now that can happen very, very, very high rate, in which case the 2D model is not so bad, but still it needs to be tested in 3D in order to make sure about it, yes.
So this very different style of plate tectonics, would that have a different Urey ratio than our model style of plate tectonics?
Let's think. So the Urey ratio is based on the modern day ratio between radiogenic heating and surface heat flow. In the early Earth, obviously the amount of heat generation is much larger. Well, it's larger. It's not much larger, but it could be in the Archaean like 2 to 3 times larger. The surface heat flow in these particular models, I have calculated them, but I haven't included them in the calculations. But they are also significantly larger than the surface heat flow for the modern day. For various reasons. Those plates are moving on average. These plates are, as you can see, they're thinner because they move faster, and therefore they actually have a higher heat flow. The mantle is hotter, so that leads to a slightly higher heat flow as well. So altogether, it's probably the effect on surface heat flow is larger than the effect of increase in radiogenic heating. So I would say that the URI ratio is probably lower than it is for the present day. If you define the URI ratio as something that could change over time rather than the modern day value. Yeah.
Okay. There are other ways to recycle the surface of a planet or the crust into the interior without plate tectonics.
Mm-hmm.
And Io, Jupiter's moon, I guess, is a nice example of this, where you bury the surface and effectively reduce downward. Is there anything in the geologic record that tells us early Earth did not work like Io?
Yeah, it's a good. It is a nice way, yes. I'm not aware. I mean, so what that requires is a lot of volcanism to take place, right? Enough volcanism, enough to basically bury most of the surface of the Earth with new volcanism that buries the previous surface. Is that right?
It doesn't have to be exactly like Io. You just need some mechanism for crustal thickening, so you start making eclogenic drips at the bottom.
Yes.
Well,
yes.
Any eruption is going to bury stuff underneath.
That's right, but usually on a very local scale. If this has to replace a global mechanism like plate tectonics, it has to be on a much larger scale as well, like on Io.
At the time, I think Earth loses about 5% of its heat to the advection of magma in the form of plate.
Mm-hmm.
And on Io, that number is about 100%. And so as you make more crust, right, you're transporting more heat from the plate. And that Io-like mechanism becomes progressively more important for that.
Yes, yes.
At some point, it may dominate.
Yes.
I don't know if it has a geological signature or if it's important to how recycling happens, but you can still recycle without plate tectonics.
Yes. Yeah, that's true. Yeah.
Sort of impact erosion. There's a few people out there that think that early massive volcanic loss may be responsible for including here. I don't know what the latest thinking on this is. Right here. On the Earth, yeah.
Volcanic eruption.
But to come back to your original question, I'm not aware of any observations in the geological record that would support this.
Well, you've got Venus. I mean, how Venus looks. So there must be a way to get rid of heat and all.
Yes, that's true. Actually, there is a study by Van Tienen in 2004 that suggests that actually, in order to cool the Earth, you don't really need plate tectonics. There are ways to do it, but you need at least 10 times the amount of magmatism that we have today in order back in the Archaean, in order to maintain enough release of heat to at least compensate for the heat generation in the interior.
Mike, there's actually a recent paper by Proterozoic for steel, and technically also calls it essentially the volcanism, how much heat that volcanism can help release in addition to tectonics. So I remember the number was like 20%.
Mm-hmm.
We can actually get that much heat out.
Nakagawa. Yeah.
Yeah, I mean, to the extent that there is a geologic record or lithic record of the Thean, the answer to my question is no. That the observation we have of the old Zircons is that they can't have formed in a subduction type environment. So I don't know whether.
Well, that's what my question was, because you bury the surface with magma, you end up with a colder lithosphere. You're effectively moving crust downward.
Yes,
so
but
the eruption rate is big enough, you end up with high pressures and low temperatures.
But is that also a mechanism to bring water deep enough? Because it's
I've got a couple of thoughts. Spoiler alert. The answer is no. Well, I'll talk about this Friday.
One of the geological observations you can add here is the Slater Craton. In the middle of Canada, it's got rocks back to 4 billion years old. It's got an imaged subducting, we will call it subducting. It's got an imaged inclined boundary layer.
Yeah.
It goes down into the middle upper mantle, so 100 kilometers. So it's both the seismically imaged and the conductivity image.
This one you're referring to, yeah.
It looks like this, except so it know the stratigraphy of the mantle above it because the mantle is endless from the whole area. Directly above it is a zone of really depleted mantle, the type of thing you would expect to see in a subduction zone wedge. And in that wedge are diamonds that are 3.5 billion years old that contain isotopic remnants of subducting crust. So here's an example of a dipping reflector. It looks like a subduction zone that's 3.5 billion years old that took fluids, meaning diamond, carbon, and crustal materials down to 150 kilometers deep in the mantle. And that sounds like subduction to me.
Yeah, I agree. Sorry, there was a question, or?
You don't need to answer.
Yes, Dave.
One other thing that sort of indirectly supports subduction is those commodite temperatures that are meant to represent the hotter part of the mantle, so maybe more indicative of the bottom thermal boundary layer.
Like a present-day mantle plume kind.
Yeah,
Mm-hmm.
an analog to the present-day mantle plume. And so in order to get stronger plumes, you need to have more symmetric boundary layers. In a one-plate planet.
Sorry, a more symmetric boundary.
Yeah,
okay,
so
it's a boundary layer.
like
Yeah.
what Mike was suggesting with like hitting in heat pipes or one-plate planet, that would not result in any kind of stronger plume or strong plume activity from the core mantle boundary, and it also wouldn't cool the core very quickly.
Well, that could actually have the bottom part of that lithosphere being formed that way could drop off and sink to the bottom of the mantle and could still form a boundary layer there. I mean, as long as you've got some cold material going from the top to the bottom, I guess you can form a boundary layer at the core mantle boundary. I guess, but yeah, I agree. It's probably not as straightforward as a subducting slab would be, because that material is already going down rapidly, falling into the mantle so yeah, it's more likely to make it as a thermal anomaly all the way to the core mantle boundary. Yes, you're right.
I think we should let our speaker off the hook.
Thanks.